Here. So I'm Pete Berry from WHOI, and I'm co-chair of MD&E along with Adam Kent, and we've recently taken over for Diana Roman, who's sitting right here in the front row, who did the heavy lifting for the last few years. So yeah, we're just really excited to give you an overview of the topics we've been thinking about over the last 2 or 3 years, and the motivations and kind of our approach to thinking about these problems. So yeah, just to start off with the motivation, why study magmatic drivers of eruption? Well, first and foremost, we want to make scientific discoveries using this integrative approach. And I think that's really what this meeting is about, is bringing folks from different communities together to make progress in studying subduction zones from this truly integrative approach. We want to connect the most hazardous volcanoes on Earth to the underlying subduction drivers. And there's also a societal need in the sense that volcanoes are hazardous, and there's potential for forecasting. Something like 800 million people live in the regions that are directly exposed to volcanoes worldwide. The vast majority of these occur in subduction zones, so these are really important areas to study. And then finally, final motivation is there's many mineral and energy resources that are concentrated in subduction zones. So with the motivation in mind of why we want to study volcanoes, if it's not obvious, we can move to the sort of the big picture questions that our group identified over the last few years. And they can be broken down into 3 main questions. How do transcrustal processes initiate eruptions at arc volcanoes? And then we also want to learn about magma supply rate and the depth and distribution of magma. Now, a common theme in all these is understanding eruption cycles at restless volcanoes and at the arc scale. So really being able to focus in on the cycles and the scales that these various processes happen at to address these kind of main questions. So this is the first figure that it appears in the magmatic drivers of eruption chapter, where we're looking at depth as a function of time, right? So here we can really focus in and look at some of the processes that are really exciting for volcanologists: mantle melting, melt accumulation, the role of volatiles in magma transport and recharge. And it's interesting, that we cover this huge spectrum from seconds and minutes all the way up to millions of years. So, not all these are problems that are only addressed by magmatic drivers of eruption and people that study volcanoes. Many of these things like earthquakes and slope failure are addressed by the other working groups that you've already heard from today. But yeah, really what we're focused in are these transcrustal processes. So we have this nice little cartoon over here on the right where we see a subducting slab going down, melting. And then this is sort of the region that we're interested in, where we have magma passing through crustal sections and how that magma is stored and generated, and ultimately what leads to eruptions in subduction zone volcanoes. So this is our hypothesis grid. So the point of putting this up is, like many of the other folks did, was not for you to read everything on here, but just kind of to show you the approach that our group took in identifying those big questions about magma supply rate and the role of volatiles, the distribution of magmas, and then being able to step through the process to develop really succinct hypotheses, right? So if we know what the big questions that we're asking are, we can think about what kind of precursors we might identify to see those processes, how these processes might manifest in intrusive and extrusive systems, so studying plutonism versus extrusive volcanism. And we can also think about the various types of eruption styles. So don't worry too much about the details here, because on the next slide, I've repeated the questions here and then kind of boiled it down to the 3 main hypotheses that we're trying to address as a working group. Hypothesis A is gas and magma composition and how they're linked to eruption precursors, run-up times, intensities. Hypothesis B, mantle magma production and supply rates govern the intrusive and extrusive mass budgets, repose time, magmatic architecture. And hypothesis C, which is periods and drivers of different external eruption triggers exist over timescales of minutes to hundreds of thousands of years. So sort of that first diagram that I showed you, which was showing the huge range in time that these processes occur over, and how it's really important to understand not only how individual events happen, but how those processes are all linked together. And that's something that hopefully we're going to be addressing as part of SZ4D. So yeah, you guys have seen a couple traceability matrices already today. And again, I'm not showing this so you can read all the text on here, but I wanted to show you our process. And you can see that there's a common process in all of the various working groups of how we would go about devising our hypotheses and how we would begin to ask the questions. So again, you could start with that high level question, which you've seen a few times already about transcrustal processes. And then you can move through to looking at the specific science goals, quantifying magma fluxes through the crust to eruption, and then step through to the specific project objectives. And this is kind of critical here as we start to think about what are the measurements that we'd want to make, what are the measurement objectives, and then what the actual requirements be to make those measurements. So with that information in mind about the various measurements that we're interested in making, we can move to what we call the notional experiments. And this is actually, what we've spent a lot of time thinking about. What if we did want to monitor volcanoes and we did want to make these really important measurements to address our fundamental science questions at a series of volcanoes, what would that look like? And, I have 4 boxes here. The 2 that I really want you to focus on to begin with are the sparse sensor arrays, which would be deployed at a number of volcanoes, maybe 30 to 50 volcanoes, and then a more dense array, which would be located at fewer volcanoes, volcano pairs, and various arc settings. We're also interested in studying exhumed systems, plutonic systems. We're also interested in having rapid response array, something where if there was a significant eruption, that we could very rapidly move and instrument that volcano. So the key is here that these sensor arrays really address the transcrustal question 1, and the more dense arrays kind of tell us about the magma architecture, depth and distribution, questions 2 and 3. So I'll just jump back to those so you can remind yourself of what our driving questions are. There they are, 1, 2, and 3. I just kind of repeated that. So yeah, to go in like a little bit more detail about the type of instrumentation that we would use. Again, this is our sensor array. It would be potentially deployed at 30 to 50 places over, and they would be like 10-year deployments with, here's are just a few examples of the kind of things we'd like to deploy. Be everything from seismometers to webcams and DOAS and multi-gas. So all sorts of measurements that would enable us to really understand and capture an eruptive event. So I think this is one of the keys to the sensor arrays. We'd like to capture that entire eruptive cycle. And here's a figure that's in our chapter, which is because you might ask the question, well, what's the actual chance that you're going to capture eruptive cycle? And so we did a little bit of homework, and we looked at the Karn paper about the 99 actively degassing volcanoes. And so this is a plot just saying, if we went to the 100 most active volcanoes between 2000 and 2009, 06 to 15, 2010 to 2019, what would be the likelihood of capturing one of those complete eruptive cycles? And the answer is it's really high. If we had deployed volcanic sensor arrays on all those volcanoes, we would have captured about 30 full eruptive cycles. So you can do the back of the envelope math on that. If we are proposing to instrument 30 or 50 volcanoes of our choosing, we have a very high likelihood of capturing one of these eruptive cycles, which is one of our main objectives, and that's really the driving question number 1. And then the imaging arrays, again, these are much more dense arrays, but over fewer volcanic sites, and we would envision that. Yeah, that these would be deployed in each one of the arcs that we're going to focus on, and these will really be useful in addressing our questions 2 and 3, which have to do with magma production, magma supply, the distribution of magma in these systems. So you don't necessarily need to capture an eruptive cycle, but more looking at the architecture of an entire arc system. Yeah, and so you've already heard a bit about where we're interested in going. The Chilean arc was a really excellent place for us because It supported all 4 of our notional experiments. So the sensor arrays and the imaging arrays that I've been speaking about in a little bit of detail, as well as the rapid response and the exhumed systems, we'd be able to address or to enact all these notional experiments in the Chilean arc. It's accessible. There's already wonderful work that's being done there by many of our Chilean colleagues. And so it's really, and it has a variety of subduction parameters, which allow us to test many of the hypotheses and address these fundamental questions that we're interested in. It's a really great place for us. So we envision that maybe 50 to 70% of the work would occur in Chile, but we're also interested in doing the other 30% in the Cascades in Alaska, in the Aleutians, which are active but very remote. And of course, the Cascade arc is less active, but in proximity to a very large population, so potentially very important. Okay, so phasing, we're somewhere, I think Emily said we're going from phase 0 to phase 1. So, we're in the process of community building. That's what this workshop is all about. We're going to have a chance to interact in person and have these really good conversations. And then we'll move into hopefully planning the initial field programs, and then moving into more focused field programs that pertain to the sensor arrays, and eventually a full rollout. So this is sort of how we envision the next several years going. And I also just want to note before I wrap up that there's also, it's not all about instrumenting volcanoes. We're also are interested in, we're generating data from all these instruments, but it's going to be about how we integrate and interpret that data and the kind of modeling effort that we make afterwards. So in addition to instrumentation, there's a large component of field geologists being in the field. There's folks doing experimental research back in their labs. When we have all these data, how do we integrate it all together? So this is going to be really critical to the magmatic drivers of eruption objectives, is integrating everything together in these various numerical models and inverse data simulation, and eventually also the importance of capacity building, which was already touched on in the first talk. So with that, I'm sure everyone's ready for lunch. And I will thank the folks that most recently served on the Magmatic Drivers of Eruption Working Group. This is not an exhaustive list. I think there's actually people that came and went beforehand. And I will also welcome, this is the most up-to-date list recently, and I'll welcome some of the new members, and you can see that there's a bit of overlap. So if you see a name badge with these folks, please come talk to us about volcanoes and magmatic drivers of eruption. We'd be happy to chat with you more about the science. So thanks very much.